start with a couple of homework questions, and if there are more, I'll take those too, and then we'll jump into sample distribution stuff we were talking about last week. The first question was regards to, I don't know what this random variable is, but it had a mean of 56,000 and a standard deviation of 400. And it asked the question of, can you find the first quartile? Does anyone remember, is this going to be a forward or a backward calculation? Backward. It's going to be a backward. Sorry, it's going to be a backward calculation. So, picture. Where is the first quartile going to be? What should I be looking up?
To 25%.
Yeah, 25%. That's right. So the first quartile is basically saying we want to find the x value at this of 25%. And so what should I do first?
Look up the area.
Look up the area on the table. That's correct. Here's one. Is it going to be on the positive or the negative side? The negative. It's less than 50. So we're looking for 25%. Find it. Looks like it's right in between these two. So negative 0.68, negative 0.67. And then where we go from there, what do we do? Now we'll find the x. Do you have a way for me to do that?
Yeah, you do square times deviation plus.
So since we have those things over here, we have negative 0.68 times 400 plus 6,000. And whatever that comes out. Once you see it. Alright, and how about the second one down here? The idea for this one was that we wanted to find the probability between, or the area between 4K and 7K. And we have this random variable that has a mean of 5,000 and a standard deviation of 1,500. So what should we do? Is this a forward or a backward calculation? Forward, right? We're getting the x values, it's forward. And so where do I start in forward calculations? What do I do first? Find the z's. So I'll calculate z1. If we imagine the picture, there's 4,000. Or sorry, there's 5,000. And then basically we want the proportion between 4K. We want this area. Okay, so we'll find two z's. So 4 minus 5 over 5. 7 minus 5. 5. Okay, and then what do I do with this? So this is like 0.67 and 1.33. And one of these, this one's negative, right? Okay, what do I do with this? Subtracting.
Add on the x, right?
So the x values were 4 and 7.
So you always use 4.
So I'm using these scores.
So when I did this the first time, I subtracted the z-score for the 7,000 minus the 4,000.
We don't want to do that.
We don't do that.
We don't want to subtract z-scores,
Alright.
right? Because these are still just marks, right? These are marks. Like here's negative 0.67. Here's 0. Here's 1.33. And we want this area. This is like on the z scale. This is on the x scale over here. So what do we want to do? We don't want to take the difference of those z-scores.
Do you want to look at the percentages?
We want to look up the percentages, that's right. So we want to look up the percentages. So the negative 0.67, we're going to find those z-scores on the outside. So here's negative 0.6, 7 is at the top here. If you go to where those two things match, you get 0.25143. 0.25143. Where is that on this picture? Okay, and where, like, over, because this is an area, right? So is it like over here? It's this part right here. It's this unshaded part. Okay, and then I look up 1.33. So here's 1.3. I want the last digit to be a 3 as well. I go to where those two things match. I get 0.9042 or 84. And where's that on this picture? So here's the 1.33. Where is that shaded region?
The entire area to the line.
Yeah, it's like all of this area over here. It's like if I were to shade all of this. So basically everything from here over is the 0.9084. Everywhere from here over is the 0.25143. So if I want this middle part, what should I do? Yeah, just take the difference. So 0.25143. And we get something like
0.65681.
0.6568. Or 65.7%. Any questions about these? Any other homework questions?
16,
What was that?
that the company produces light bulbs, the lifetime in hours of light bulbs have a normal distribution within 1200 hours, and extended duration of 100 hours.
Okay. And then,
And then we can determine that 2.5% of the bulb lasts longer than how many hours.
so this was the tricky one on the thing that we did last week. So what does my picture look like here? So where's this 2.5% at? On the left or the right? Okay, and then where do I shade? So this is going to be the area where 2.5% of the light bulbs last longer. That doesn't look right.
You want to do the right side.
So it'll be the right side. And now where do I shade?
To the right.
To the right. And here's like the mean of 1200. Standard deviations 100. Right, here's the mean of 1200. Standard deviation 100. Right, and if you came back with this one, if you got this number over here, the idea is that this doesn't make sense because you're going to get something less than the mean. We know that 50% lasts longer than the mean. And so if you came back with some value over here, way more than 2.5% lasts longer than that. Does that make sense? So even if you hear this picture, it's like, oh, okay, now I realize that doesn't make sense. Okay, so we really want to find this one. And I think these use the approximation rule. So what part of the rule are we using? What is it?
The positive side.
Well, the positive side. 68, 95, 95. That's right, we're going to use the 95. And so how far away should this be?
Plus 2 standard deviation.
Plus 2 standard deviations. Right? So 1200 plus 2 times the standard deviation is 100. Right? And if we go 1200 minus 2 times 100, the idea is that this area and here is going to be 95%. And so that leaves the 2.5% we're asking for in the right hand. So that maybe okay. So then it's just so 1,400 hours. Be the answer. So 2.5% lasts longer than how many hours? 2.5 lasts longer than 1,400 hours. Yeah, go ahead.
And where did you get the 2 from?
Yeah, so Yeah, so this is using the approximation rule. So it's like 68, 95, 99.7, where basically 68 is between plus or minus 1 standard deviation. So if I just went 1 standard deviation this direction, 1 standard deviation this direction, this middle region would be the 68 part.
Okay.
Okay. If I go 2 standard deviations, that is if I go 2 standard deviations to the left and 2 standard deviations to the right, then that middle area should be 95, which is where I know 2.5 will be in each tail.
Gotcha.
Yeah. And then if I were to go 3, then I would have 99.7 in the middle, and then I'd know 0.15 is on each side. Yes, that's a good question. Any other questions about that? Okay. Cool. Let's start this class very similar to how we started the last one. So who can tell me what is a sampling distribution? What's the definition of a sampling distribution? A distribution of a statistic. The distribution of a statistic. And what statistic did we say we were going to be looking at for a while? The mean. That's right. The distribution of the mean. So specifically, we will be looking at sampling distribution. For the sample mean, X bar. We'll be looking at sampling distributions for the mean. But a sampling distribution is defined as the distribution of a statistic. Specifically, we will be paying attention to sampling distribution of it. We could have the sampling distribution of any. Okay. So, again, we had 2 theorems that we discussed over the last couple of classes. What are the 2 theorems? What's the first one we're talking about? The law of large numbers. And what does that one tell us?
The more numbers you get, the more.
The closer to
The more numbers I get,
The more numbers you sample,
the more values I sample, what happens?
the closer you get to the truth.
Yeah, perfect. So it's specific about the sample mean, but basically the sample mean will converge to the population mean. Right? My sample mean will go to the population mean, and they'll get closer and closer as the sample size increases. Right? So mathematically we can write the limit as n goes to infinity, so that is as I get a larger and larger sample size, that's what this first part is telling us, the sample mean will go to the population. So we could write this mathematically in this way. We could state it in margin state. The larger your sample size, as n gets larger and larger, the sample mean will move closer and closer to your population. So that's what this says. And what was the second one?
central limit theorem.
The central limit theorem. And what does the central limit theorem tell us?
If we choose a large enough sample, our sample mean will be normally distributed even if our original data is not normally distributed.
Yeah, that's right. So if our original data, that is in X, so every problem we've been talking about, everything that was on this last homework, things were like normally distributed. This was normal with this mean and this standard deviation. This is normal with this mean and this standard deviation. Basically, the central limit theorem says, even if that original data set isn't normally distributed, so distributed in some other way that's not normal, but it has some mean and some variance. The idea is that if we choose a large enough sample size, the sample mean will be distributed normally with the exact same mean, but its spread will be smaller by basically the square root of it. So this inside part is the standard deviation, and if we square that, that's the variance. This is the part that we're going to discuss most recently about this part in the sentence. Any questions about that?
Is that squared? Is that inside or outside?
It's outside, so it's like this whole thing squared. Okay, so the thing that we end up working with in a lot of our calculations is going to be this inside part. We don't actually care about squaring. That would be if we have the variance. So as long as n is, what we'll say is large enough, and for this class, we'll frequently call that n greater than or equal to 30. If we take a sample size of 30 or more, then we'll assume that the central limit theorem is kicked in, and that our sample mean will be normally distributed. Okay. So even if this isn't normal, we can get normality here with a large enough sample size. Alright. So, let's actually state a couple of other things about this. So one thing worth noting is that the central limit theorem isn't necessary if our original distribution is normal. That is, if x is normally distributed up here, I don't need a large enough sample size for this to be normally distributed. X bar will be normally distributed just because this was. Okay, so this is normal. If x is distributed normal. X bar will also be normally distributed, and that's because the original distribution was normal. I don't need a sample size of 30. I could take, right, x is basically just sample sizes of 1. I could take sample sizes of 5. I could take sample sizes of 8. Some things less than 30. And still have normality of x bar. So we don't need the central limit theorem if this is normally distributed. Okay, we're not using it. We can do normal distribution calculations without it. We'll see that in some of the stuff we do today. So that is, if x is normal with some mean and some variance, x bar will also be normal with the same mean, and this still happens. And this is kind of like regardless of sample size. So this happens, right? We move from this to this regardless of our sample size. We'll see this in practice, but it's worth noting. And that means we're not using the central limit theorem in most cases. We just get normality because this was normally distributed. We don't need a large enough sample size. We don't need to use the central limit. So. start on the side that looks like this. It's the same thing, just squares. Not the one that has a problem level 4. Alright, so this first question says, assume we're interested in studying the filling process of the Skittles machine. We know that the number of purple Skittles in any given package follows a normal distribution with a mean of 13 and a standard deviation of 2. So, here's the relevant information. So basically, the number of purple Skittles, right, so X, in my case, is going to be number of purple Skittles. Okay. And what we know about X is X is normally distributed with a mean of 13 purple Skittles per pack and a standard deviation of 2. So X is the number of purple Skittles per pack, and it has these characteristics. Okay. All right. The first question says, if possible, find the probability that more than 16 purple Skittles are in a randomly selected package. So how do we do it? It's a forward calculation. It's just like what we did before. Does everyone recognize this? It's no different than what we did before. So we can imagine we have this mean of 13, we have a standard deviation of 2. We're asking what's the probability of more than 16. It's a forward calculation, so what do we do first?
You look for the z-value, so x minus, or 16 minus 13 over 2.
16 minus 13 over 2.
Yes.
So that gives me 1.5. You look that on the table. 1.5 is over here. We want the last digit to be a 0. And so that gives us 0.93319. And is that our final answer?
No.
What do we need to do? Subtract that from 1. That's right. So this part is just that unshaded region. That's what this part is. And so 1 minus that will give us this part up here. That's like 7%. So that's going to be the shaded area over here. Is that okay for everyone? What you're already sort of comfortable with? Okay, then 2 says, can you find the number of purple Skittles so that only 2% of the packages contain less than this amount? So this is similar to what we did earlier. So, where should I mark? What should this look like? Should it be on the left or the right? So, if we did mark on the right, where would I shade? Yeah. It says we want to find where 2% is less. And so if we started shading, we shaded on the right, like this is going to be way more than 2. So we'll want to shade over here. So it should be some mark so that only 2%, some small amount, are less, right? This is telling us how we shade. So here's 15. So now what do we do? This is a backward calculation, so what's my steps? What do I...
Look for it up 2% on it.
Okay, is that on the positive or the negative side? That should be on the negative side. We're looking for 2% in the middle. So,
Negative 2.05.
negative 2.0. Yeah, that seems good. So negative 2.05, negative 2.06, either one of those would be okay. We have negative 2.05. And then what do I do from there? What's the next step?
Multiply that by the standard deviation.
Yeah, we'll solve that for x, so we multiply that by the standard deviation, which is 2, and add 13. So we get like negative 9-ish, or sorry, 9, not negative 9. Right around, or 8.9 Skittles. 9. So that's like the number of purple Skittles we can expect to get less than 2% of the time. Or, yeah, 2%. Is that okay? Any questions about that? All right, so those should be reviewed. Now in step 3, assume we randomly select 7 packages and find the average number of purple Skittles in these packages. What is the distribution of the mean of 7 packages? So notice the way that the wording changes for this particular problem. It says, what is the distribution of the mean of 7 packages? So what are they talking about here?
Sampling distribution.
It's a sampling distribution, that's right. So everyone notice in these first ones it says, find the number of purple Skittles so that only 2% of the packages contain less. That's talking about the original distribution of the Skittles. Everyone see that? That's talking about X. And then similarly up here, if possible, find the probability that more than 16 Skittles are in a single package. And so that's talking about X. Right? It's talking about each package. Whereas here, this is talking about the distribution of the mean for 7 packages. That is, you take 7 packages, you average how many purple Skittles there were. You take another 7 packages, you average how many purple Skittles, just like we did in the sampling distribution on Wednesday. Does that make sense? And then we're asking, like, where is the average going to fall? Where's the average of 7 of these things going to fall? So you can imagine, yeah, getting 7 of these things, averaging the number of purple Skittles. Then someone else gets 7 packages, they average their purple Skittles. And you're asking how those fluctuate. Is that okay? So we randomly select 7 packages, we find that the average number of Skittles, and we want to find that average. What is the distribution of the mean of 7 packages? Okay, so that is asking about the sample distribution. So how is this going to be distributed? It's going to be normal.
Normally.
Okay.
Because there's
So why is that?
How's this done earlier in the direction?
Because of what?
How's this done earlier in the direction?
Yeah, because the original distribution is normal, right? Since X is normal, right? Since this is normally distributed, this is also normally distributed. Does that make sense? The original draws are normal. So if I take 7 of those and average them together, that's also normal. Okay, so this is normal. What will this be centered on? What will be the mean of this distribution? It'll still be 13. Right? It'll be the same as the mean for this, right? Since this mean up here is 13, right? Here's the mean before. This will be centered on the exact same point. So going back, it looks like this. Right? We're in this second case. So we have this. This was our original purple Skittles per bag, was this. And now we're talking about the sampling distribution, so it'll follow these characteristics. So since this was 13, this will also be 13. Then this was 2 squared. So this will be 2 divided by, what's this part? 7. Yeah, the square root of 7. This will be like 2 over root 7. And basically, so it says, what is the distribution of the mean of the 7 packages? And so I like to write things this way. You can definitely write things this way if you want. But basically this says it's normal. It has a mean of 13. And it has a standard deviation of 2 over root 7. So the sampling distribution, the distribution of the mean of 7 packages, has these characteristics. I prefer to write it this way because I resonate with just pulling things out of this part. But if you want, you can write it out in words. If we were to take a sample of 50 and we asked about that mean, it would be 2 over root 50.
well, do you have to square the 2?
We're not, so similar to the way that we didn't deal with like 4 here, similar to the way that we didn't square this to work with it,
Okay.
we're not going to square this when we work with it.
Okay.
Then it'll give you a variance. That's correct. So 4 says, can you find the probability that the mean of 7 packages is greater than 16? Yeah, so the probability that the average of 7 packages has more than 16 per package, so that average is greater than 16. Okay, so this is again talking about the sampling distribution. Does everyone see that from the wording? it's talking about this mean of 7 packages. And so when you write things in this notation, to me it seems easiest because then I just look at which distribution I'm using and I pull from that part, right? So if I'm dealing with this distribution, I look and I see, yes, it's normal, so I can do normal distribution calculations, and then here are the characteristics that I need to use. If I'm dealing with the sampling distribution, it's normal, and here are its characteristics that I use. Okay, so anytime I do a forward or a backward, I'm using these numbers if I'm in a sampling distribution problem. If I'm in the original distribution, then I'm using these numbers here. So, find probably that the mean of 7 is greater than 16. Mean of these 7 packages is greater than 16. So, talking about X bar, it has a mean of 13. And we want to find probability greater than 16. Okay, so before we even find this, what is your intuition in, just based on what we did last week, on how this area should compare to this area up here? So should it be greater or less than the 7%? Should be less than. Sorry, I don't know where that came from, but it should be less than. And do you have any intuition for why that would be the case? Okay, go ahead. Yes. So mathematically, this becomes smaller, and so therefore there's less spread, right? So it becomes more peak. And if you remember from the activity we did on Wednesday, when we looked at the spread of the original numbers, they went from like 60 to 78. And then when we had those numbers up on the board, they shrunk down, and it was like nothing went up to 60 or 78. They were all like towards the middle. Does that make sense? And so there's less area in the tails of this distribution. There's more area in the center. Does that make sense? So you're right, but this will be less, and it's mathematically you can see it here, right? You're going to have a smaller number. Intuitively, remember, like when you're dealing with these sampling distributions, things group around the mean. They group around that average, and so fewer things are out in the tail. The probabilities in the tail are smaller. So how do we find this? What are we going to do?
Forward.
It's a forward calculation. It's right. Basically the same thing that we were doing before. So I'm going to take 16 minus 13, except for what's going to change?
2 over square root of 7.
That's right. I will just have this part in the denominator now instead of just the 2. Right? The idea is that if I'm talking about the average of these 7 packages, they follow this distribution. And therefore, since their spread is like this, I have to use this down here instead of just 2. Does that make sense? So this is going to give us
I got 4.0 as the answer.
4?
4.0.
4.0?
Yeah.
4.0. All right. So on the z-score scale, you're like 4. And we'll lose this area. And if we go to the table, it only goes with 3.33. So we're off the table. What happens?
Turns into 100.
So which part of this is 100?
The left.
Yeah, this part's 100.
So basically
This part's
there's
100.
100.
And so what's that means out here?
0% chance.
Yeah, basically nothing is out here. So no tests are starting on fire. It's not
Wait.
undefined.
Sorry. It's 0 because it's not empty.
It's just undefined. Because you went off the, so you can imagine 3.39, right? So 3.39 is the last number on the table. And it tells you the area to the left of that, right? The area in this shaded region is 0.99965. So 3.39. You can imagine that's like over here somewhere. This area left of that is 0.99965. So there's even more area to the left of 4. And so if you're to the right of that, I mean, for all rounding purposes, there.
Can you bring it down a bit?
Yeah, sorry about that. Yeah, so 0.9965 is the area to the left of the 3.39. And therefore, if you're to the left of 4, there's even more area. And therefore, the area to the right of it, these are all not zeros. This is just 0. Is that okay? Any questions? So if you go off the table, essentially, for any test taking purposes, your answers are 0 or 1. Right? And it's just based on how you shape it. So then 5 says, does it worry you that your sample size was only 7? Are we using the central limit theorem to define the distribution basically that we defined in part 2? So, okay, so
I'm not worried.
do we use the central limit theorem? Okay, so no. We didn't use the central limit.
No, because it was distributed normally.
Yeah, and I think I heard the answer. So why?
It was already distributed.
Because x is already normal. So we didn't use the central limit theorem because that's already normal. And therefore, this sample size of 7 also shouldn't work, right? Like, the idea is we need a large sample size to get normality to do these calculations. But the sample size of 7 is fine in this case because we already have something that's normally distributed. Yeah, go ahead.
So you were saying earlier that, for example, if this wasn't normally distributed, we would need something greater than 30, a sample size greater than 30.
Yeah.
essentially.
So for this class, we'll use sample sizes greater than 30. In practice, you know, it depends.
Right.
People have shown that with most distributions, if they're just like regular right skewed or regular left skewed distributions. 30 is large enough for your mean to still take on normality. Just via simulations, people have shown that. But
For this class.
yeah, for this class, that'll just like always be the case. If you have something that's only slightly right or left skewed, you might only need like 10 or 15 for X bar to be normal. If you have something that has like 4 modes and like is skewed multiple different directions, you might actually need a sample size of like 50
Yeah.
for the central limit theorem to kick in. The central limit theorem just guarantees that if you have a large enough sample size, you get normality of X bar. What that large enough sample size is dependent on the distribution of the original data set. So for this class, we'll just kind of plainly use.
Sweet.
Yeah, go ahead.
For number 3, I have a question. So it's asking for what is the distribution. When you like ask about those questions, do you want us to give an answer like the mean and the standard deviation?
Yeah, so technically you could probably just say normal. And then a lot of times on exams, to be explicit, I'll have like 2 other parts and we'll say, what's the mean of the sampling distribution? What's the standard deviation of the sampling distribution?
Okay.
So the first question might be, what is the distribution? And then the second might be, what's the mean of that distribution? What's the standard deviation to get these parts?
Okay.
So,
Yeah.
yeah, because this isn't explicitly asking for these. It's really only explicit about this part. Okay.
And why don't we worry that the sample size is only 7?
Okay, so, we would need a larger sample size. So, we would need a larger sample size for normality of our sampling distribution if X wasn't already normally distributed. But that 7 doesn't bother us because X wasn't normally distributed in this case. Any questions about this? Let's try the other side.
So the curiosity is, how are you gonna lay out the tests?
Yep, so the tests, so the tests, our first test is coming up in about 2 weeks or something like that. We'll talk about this more during the review, but essentially I don't do multiple choice and true false. They're usually about 5 pages, and so each page is like a question, like a main body of a question, and then it'll have like a bunch of subparts. And then the next page will have like the body of a question and then a bunch of subparts. Yeah. So you can imagine essentially something like we just did. Right? This could be, there might be like 1 or 2 more subparts in here or something like that, but this could be like 1 page of the example.
You said 5 pages?
Yeah, usually they're about 5. So you can imagine like a sampling distribution question, a normal distribution question, a population parameter sample statistic question, something where you're calculating like 5-number summaries and stuff like that. Something where you're talking about like shapes of distributions. Maybe something about variable types. Yeah. So, this one's got a lot of words at the top. So I'm just going to try to pick out the parts that matter from there. Okay, so in determining place orders of product inventories, retailers look at this thing called lead time, and then basically they give a description of what lead time is and give a resource. We're interested in the average lead time, for a particular supplier of men's apparel, and so this purchasing department of a national department store chain randomly samples 50 supplier lead times, and they find an average of 44 days for their lead times. The lead times for that particular supplier are known to follow a normal distribution with a mean of 40 days and a standard deviation of 4. So let's see here. So I'm going to pull this part. Lead times for this particular supplier. Okay, so lead times for this particular supplier are known to follow a normal distribution with a mean of 40 days and a standard deviation of 12. So I'm going to write that like this, where X in our case is basically lead times. So X is lead times. They follow a normal distribution with this mean and this standard deviation. Can someone tell me, there's also this number floating around? Right, so there's this, right? There's this part. How would I label this? How would you give mathematical notation to this 50? What's that?
N?
That's N. That's right. That's N. Right. So the department store randomly samples 50 lead times. Okay. So this is like
This is total count.
yeah. That's like the sample size that they choose of these lead times. Because they could obviously use any lead time for any of their products.
Right.
But then this one's more, so they found a sample mean of 44 days. So what is, like, should that, did I do this wrong? Should this be 44? Should that?
No, that's the mean of that N.
That's the, yeah, that's right. This is the X bar specific for that N. That's exactly right. So this is an X bar specific for this N. So if we think back to Wednesday and the sampling distribution activity that we did, this 44 is like one of the X's that was on the board. Does that make sense? One of the X's could have been 44. It could have been just like when we were measuring, like some of you had like 67.3, and that's one X bar of your 5 draws. This 40 is like the center of that entire distribution. It's the mean for all of those X bars. Does that make sense? So this is like the center of that distribution that we had on the board. Whereas this is just like one X bar. It's one of the X's that was on the board, not the center of all of them. So this, I would like to notate, this is like mu X bar. This is the mean of all the X bars. Or the mean, actually, and this is the mean of X at this point, which is going to be the same as the population mean, whereas this is just a single X bar. Is that idea, that can be confusing. But the idea is this is like one of those X's you drew on the board. This 40 is the center of that entire distribution of all of the X's. So, all right, so part A, so just jump right into it. So they say specify the mean and the standard deviation of the sampling distribution. So, what do I have here? What's this? Is this the sampling distribution?
No.
No.
It's X.
Yeah, that's the distribution of just wait time. So what is the distribution of the sampling distribution look like?
X bar is distributed.
X bar will be distributed
normal,
normal.
and the mean is 44. Wait. That's X bar. Hold on. 40.
Is it 40 or 44?
I vote
Is it 40? It's 40, right?
40.
Yeah, that's right.
I go 42.
Sorry.
So it's going to be, right, so from our notation, the idea is like, however you distribute this, this is the center of that distribution. This will be the same, right? So since this was 40 here, the mean of all the lead times is 40, and therefore the mean of the sampling distribution is also 40. Does that make sense? And this could, right, any one of these X bars, they're still random, right? I choose 50 lead times, I take the average, that could be 44. I choose another set of 50 lead times, I take the average, that could be something else, completely different, not necessarily 44. This is like the mean of all the lead times. It's considered to be, if you looked at every single lead time, the mean of them is 40. Does that make sense? Okay. Which isn't super realistic in practice, but we're still learning how these things work. So 40. And then, how about the standard deviation? What's that going to be?
12 over square root of 50.
12 over root 50. That's right. So the standard deviation is that inside part, and if we squared it, that would be the variance. Go ahead.
So, like, you obviously write the square, you know, the 2, but you don't do it.
You don't have to. You can leave the 2 off.
Okay, that kind of confuses me, right? Then I'm like,
Yeah, you're like, you never use the 2, so if you like just using the standard deviation, go for it. And I will say, some people notate them either way. Some people notate it with just the standard deviation, they leave off the 2s, and then some textbooks use the 2 up there. I just do it for consistency. Since I'm always writing the variance, I'll continue to do it, but if you don't want to, feel free to leave it off. Okay, so the mean, so it says specify the mean and the standard deviation of the sampling distribution. So if I had to, this right here, this is the mean of the sampling distribution. This part right here, just this inside part here, is the standard deviation of the sampling distribution. So I can label those as like mu of x bar and sigma of x bar. That makes sense?
So would you accept 12 over the square root of 50 as the answer for? Okay.
Yeah.
We wouldn't actually do that.
So another thing from like test taking perspective, anything that's mathematically equivalent to the right answer, I label as the correct answer. So you want to write it in decimal form, that's fine. You want, like, honestly, we went through that review question at the beginning of class where I didn't actually solve it. Yeah, this part right here. So we did this review question, and I didn't actually solve it. For a test, this would be correct, right? You don't have to get me at final answer. This won't hold for all of your classes, but for me, this is fine. Like, this is mathematically equivalent to the final answer, and I can see all of the pieces to it. Honestly, when I grade exams, I basically just go through and say, does this logic make sense? Do I think those numbers seem reasonable? Yeah, that looks good. And I usually don't have like an answer pre-written, so I just kind of like go through and like make sure your logic makes sense. And then if like this z-score seems off, I'm like, oh, okay, that's -1. Or how did you get these numbers over here? No, those aren't right. So, but yeah, I care more about like being able to see your thought process than if you get one number right at the end. That will change from teacher to teacher, but that's fine. Okay. Any Any questions about this? All right. So then part B, we actually already did this in part A. Specify the shape of the sampling distribution. What's that going to be?
Bell curve.
Yeah, bell curve or normal. Yeah, bell curve is fine. And why? So if I were to ask the question, well, part C kind of does. So does the sample size of 50 have an impact on the shape of the sampling distribution? That is, does the value of n equal 50 matter? Yes or no? Explain your answer.
No.
I would argue that you could actually answer this yes or no, just depending on how you argue it. So does someone want to give an answer of yes?
Say no, because it's this normal distribution.
Yeah, so you could say no. The lead times are normal. So we don't. Okay, the lead times are already normally distributed, so we don't really care about a sample size to get normality. Right? We don't need a sample size of 30 or any other mark to get a normal distribution. The lead times themselves are normal, and therefore X bar is normal. Does that make sense? So this is one potential answer.
Yes, it gets more accurate for the sample.
Yeah, that's right. So you could say yes. So n controls this, right? And that's part of the distribution, right? So n controls the standard deviation. And so you could say n determine spread. If n was larger,
Did you say controls the normal distribution?
I mean, it doesn't control that shape. The bell shape holds regardless of the sample size because the original distribution is normal. So it doesn't control the shapes. We have bell shapes all the time with this. But if n was larger, the distribution would be less spread out. Okay, so if n was larger, the distribution would have less spread. If n was smaller than 50, it would have more spread, right? Exactly. So it kind of determines the accuracy of X bar in the way that it estimates mean. Is that okay? Makes sense? So one of the reasons I don't like multiple choice or true false, like that, is sometimes it's debatable depending on how you think of the question. Part D says, find, if possible, the probability that a single lead time is greater than 46 days. So the first question that I have is, which distribution are we working with? So find, if possible, the probability that a single lead time is greater than 46 days. So is that talking about this or this?
A?
Which one's labeled as A?
The second one.
This one?
Yeah.
This is A? And
Yeah.
This is B?
Well, no, because it's under A.
Oh, part
That's
A.
why.
Gotcha. Part A. Okay, never mind. I was like, I don't know which is. Okay, so
No,
A, B,
no,
is this.
A, the one
So
under
this
A.
or this? Okay, so we have one vote for A. Here.
Single lead time. Makes it hard to go together.
Okay, so we have one vote for this up here. Any other?
I won't be mad if I lose.
What do you do without? Not the-
This one up here? Okay, yeah, so here, we're asking about a single lead time. Let's look at some of the later questions. So find the probability that the 50 sampled lead times have an average of at most 44 days. So which distribution is that talking about? Part E.
The X bar.
That one's the X bar, right? So part E is saying find the probability that we take 50 lead times and the average is at most 44 days. That's talking about sampling distribution. It's talking about the average of a certain number of things. F says find the probability that the 50 sampled lead times have an average of between 44 and 46. So what's that?
It's also X bar.
That's an X bar, right? Does everyone see this from the wording? So you're talking about the average of these 50 lead times. And this one is the average of these 50 lead times. So now let's go back to this one. This one says, can you find the probability that a single lead time is greater than 46? So what is that one? Yeah, it's talking about this one up here, right? It's different than the average of 50 things. So everyone see that? This is like a single draw from this distribution. This is talking about the average of 50 things being pulled from some distribution. Okay. I mean, half of the battle here is like recognizing, is this sampling distribution or is this the regular distribution? Hopefully that makes sense. This is a single lead time, so we're talking about the first one. So can we find this? Find if possible the probability that a single lead time is greater than 46 days. Okay. So how do we do it?
Do 46 minus 40.
Okay. 46 minus 40. Yeah. Divided by the standard deviation, which is 12. And so this will give us 1/2. I know what I do with that. Yeah, go to the chart. So I want to know the probability that here's 0, here's 1/2 is greater than. So we go to the table and we look up 0.5. What does that give us?
0, 0, 0.
Goes 0, 0, 0.
0, 0, 0.
Wait, what?
Oh, wait, am I on the wrong side? Oh, here.
Ah, no, that doesn't sound right.
162,552.
0.655.
162,552.
Well, it's a negative. No, I'm not negative. Just kidding.
Point.
I'm
Be
kidding.
positive.
Yeah, I'm kidding.
162,552.
1, 6,
0.65.
9,
It's
1,
not-
4, 6.
9146. That seems reasonable. Any other people getting this?
That's the right.
That's the right number. Okay, what are we looking up? Where are we finding this? We're looking for 0.50. Where do we find that on the table? On the outside, this is the z-score. So we're looking at 0.5 along the left margin, and then 0 across the top. Go to where those two things meet, and we get a number. Is that our answer here? We have to do 1 minus that. We need to do a 1 minus that because we're looking at the area greater than, which is this part over here. Is that okay? So this should be about, yeah, 31%. 30%. Is that okay? Any questions about that? Okay, part E says find the probability that 50 sample lead times have an average of at most 44 days.
That's what I did wrong.
So what's this picture look like? What am I doing? Is this forward or backward? Maybe we're still stuck on the last one.
Yeah, give us a second.
Backwards, sir. Are there any questions about it?
44 minus 48.
That's true for this one. Pretty cool. Other questions about D? Are we still stuck on D? Okay, so we calculate the z-score. We find the z-score from the table, 0.5. So here's 0.5. We want the last digit to be a 0. That gives us the 0.69146 right here. What part of our picture is that? What part of my picture is that? That 0.69146. Where is that?
On the left of it.
To the left. It's this unshaded region. This is the unshaded region. And therefore we did 1 minus to get the right shaded region. So, are we good on this question? Yes. All right. So E, find the probability that the 50 sample lead times have an average of at most 44 days. How do we do this? What am I doing? Yeah, so we're working with the sampling distribution. And so what does that mean my denominator will be?
12 divided by
12 over root 50. That is correct. Okay, so 44 minus 40 over this. 2.35? Cool. And Where am I shooting? To the left. So it'll have at most 44 days. So at most it should hit this Z-score. And it'll be all of this part. And so we look that up on the table. 2.3. And then 5 should be the last digit. Go to where those two things meet. You get basically like 99%.
I got 6.8 for the answer.
6 for this? For the Z?
For E, yeah.
Okay. So it should be 4 divided by what's root 50 is
Root
like
50 is 7.07.
yeah. So this will be like
12 divided by
One.
second answer. 1.
4 divided by 1.7. 1.7.
Yeah, it's like 1.697.
Okay.
Oh, never mind. Oh, weird.
2.35 seems reasonable.
Yeah, it is.
Yeah. So be sure you're taking the square root, then divide the 12 by that, then divide whatever the entire numerator is by that. Right. So this part, right, is all happening together up here. So you don't want to take the 40 and divide that and then subtract. That'll give you something not right. So it's like this should all happen together. This denominator should all happen together. And then, right, this is the numerator. Here's the denominator, and then you divide as the last step. Okay. All right, so then for F is going to be similar to what we did before.
Can I ask a question about E really quick? Why did you subtract 40?
So 40 is the mean of the sampling distribution.
Okay.
So it'll be this, right? So here's, right, this, it's worth mentioning, the sampling distribution formula is going to look basically the same. It just has X bar, because we're talking about the average of something, and then basically it has that square root of n in the denominator. This mean is still just the mean of that distribution, and this whole part can basically come down to our equation. Is that okay? So I'm going to skip F because it looks a lot like these. It'll be fine. G says, did you need the central limit theorem for any of the above calculations? Yes or no? Briefly explain why or why not.
Yeah, because we used two formulas.
No, because yes and no, I guess.
And why is that?
They're all normally distributed.
Because the original distribution, because X, right, so X was, that is the lead time. So X was already. No, because X was already normal. Is that okay? All right, so I have one last question. Put H down here at the bottom. If let's say if the lead time
What's your handle? I can just go like subscribe.
okay, so if X was not, or if the lead times were not normally distributed, which answers would change above? That is the question I have. If the lead times were not normal, which answers would change above? So let's just start at the beginning. Start with part A. So A says, specify the mean and standard deviation of the sampling distribution. So if the lead times were not normally distributed, would this part change?
Yes.
What would it change to? So I still take a sample of 50. That part wouldn't change. Right? This part wouldn't change. You still have normality.
Yeah.
So even if the lead times were not normal, why would I have normality in this particular one?
Because you have a 50.
Because I chose a large enough sample size for the sampling distribution to be normal. Does everyone see that? The sampling distribution would still be normal because I chose a sample size of 50. So there would be no change to A, even if the lead times were not normally distributed.
So if it was less than 30 or a small sample, we would just have to take a larger sample, I guess.
For you to answer anything on the page.
Right.
Yeah. So you wouldn't know the shape of the distribution. You could still know the mean and standard deviation. It would just be the regular mean, and the standard deviation would be whatever the standard deviation is over the square root of the sample size. Those parts would still be true, but you wouldn't have the shape.
Okay.
Yeah. You wouldn't know normality to be true. Okay. How about part B? Specify the shape of the sampling distribution. Would this change if we didn't have normality of the original distribution? No. Right? We'd still have normality based on the same logic that we had up here. Okay. For part C, does the sample size of 50 have an impact on the shape of the sampling distribution? Does the value of n equal 50 matter? Okay, here we'd have to get rid of the no answer, right? No would no longer hold. It would be strictly yes, and it would be because we needed a sample size of 50 to obtain normality, and the sample size also controls the standard deviation. Is that idea?
So that would be, you get rid of no.
Yeah, basically no would no longer be an option, and the reason for no would now become a reason for why we would have to say yes. So we do need that sample size of 50 now to have normality. Okay. Then, part D says, find if possible the probability that a single lead time will be greater than 46. If the lead times do not follow a normal distribution, would that answer change? Would this change?
No.
Okay, so when can we use these scores? When we have a normal distribution. So if the lead times are not normally distributed, can you do this? So this would change. This is so this one, if the original lead times were not normally distributed, you can't compute a z-score. You can't find the probability this way. You don't necessarily know the data's bell-shaped. It could be right skewed, or left skewed, or have 7 modes. You don't know. So if it's not normally distributed, you can't do these z-score calculations. There are only 4 things that are normal. That idea. Okay. How about E? E says find the probability that 50 sample lead times have an average of at most 44 days. If the original distribution isn't normal, does this matter? Does this change? It doesn't change at all. This part still holds. Does that make sense? We use the central limit theorem. This still holds. We're good on E. Is that okay? And then how about F? If we found an answer, would it change? No. Right. Anything controlled by the sampling distribution is fine. Anything with regards to the raw lead times, those would change. Does that make sense? So if the lead times were not normally distributed, which answers would change? And answers that would change would be C and D. And all the rest would stay the same. Basically, D would be we don't have an answer, and C would have to be yes. That's great for everyone. All right. Any questions about this? Cool. So if you would like any of your papers, actually I only have one set of these. This is from like the first or second week.